Hello, circle. It's such a common shape. We see it every day. We know that the area of a circle is pi r square, but how many of us can prove it? Especially if you are not allowed to use calculus. It's going to be hard. The other common shapes that we see, rectangle, square, triangle, those are easy to prove. But circle, it's hard. So today in this video, what I'm going to do is I'm going to prove that the circle's area is pi r square. I will not use calculus and I will use simple mathematics but clever tricks. And I'll show you three different ways in which we will be able to prove that the circle's area is pi r square. Okay, let's start. First, assume that we have a circle this of radius r. Now, let's say we focus on this part of the circle, which is a slice, and let's say its width is delta x and radius is r. I can divide this circle into many such slices, and the sum of the areas of all those slices would be the area of circle. Correct. So all we have to do is find out the area of this slice, and we could then sum it all to find the area of the circle. Let's see. So we have this slice. Let's say these points are A and B. This is a slice, and if we have to find this area. If you look closely, this part is triangle. This area can be found. This upper part, but this part is still hard because of this circular nature of the arc. So it is still hard. And let's do something different. I'll try to move these points closer to each other. So A and B come closer to each other. Let's say they become like this. In a way, what I have done is I have reduced delta x. The new value of delta x is just this much. This is new delta x. And if you look at these points, and if they become A dash and B dash, this is how they look like. If you look at this closely now, this area, which was so big earlier, is now very small, like this. Why? Because these points A and B are very close now. So we have most of the area in triangle above, and the circular part is very small. I could continue doing this. I could bring A and B more and more closer so that they are just next to each other. They are not on top of each other. If they are on top of each other, then that would mean delta x is 0. What we are saying is delta x is almost 0, which means A and B, these points are almost next to each other. They are just adjacent. So in that case, this slice would look something like this. This is delta x. It's actually even more smaller. The area of this part. Now we could assume that because delta x is almost 0, this curved part is not there. In that case, we could find out that the delta A, the area of this part, is half base height. We could assume this is a triangle. Base is delta x, height is r. R, right? As this is in the scenario where delta x is almost 0. If I have to find the area of the total circle, I'll sum it. So sigma is equal to r by 2 comes outside. It's a constant, r by 2 sigma delta x, right? Let's see what is sigma delta x. Sigma delta x is sum of all such lengths. Delta x, delta x, delta x, which is perimeter of the circle, correct? This becomes r by 2 into 2 pi r. 2 and 2 cancel out, and this comes out to be as pi r square, right? So this is one way where we have proved that the area of circle is pi r square. We didn't use any calculus. All we did was we took this circle, we have broken it into many slices like this, each of width delta x. But if delta x is very small, these slices become like a triangle. And if I sum the areas of all such slices, I can get the area of circle, right? And at the end, you would see that all we care about is sum of these widths of these these smaller slices, right? We don't care what the value of delta x is. What we need is sum of all this. So this is 2 pi r. So in a way, this delta x didn't matter. We have pi r square, correct? That's first proof. Let's start the second one. Second, we'll use another clever way to prove that the area of circle is pi r square. Again, we will not use calculus. We'll use simple mathematics, what we already know, and using that we will prove that the area of circle is pi r square. So this is second way. Again, let's say we have a circle, radius r, this is the center. Now let's say we consider this a smaller circle with the same center, and it has radius x. And let's consider another circle next to it, and this ring's width is delta x. In a way, the outer circle's radius is x plus delta x. Now, if we can find this area, this ring's area, then I could construct many such rings like this in the circle. And if I can sum all those rings areas to find the area of circle. Correct? Now let us focus only on this ring. This ring has inner radius x, outer radius x plus delta x is width. If I cut this ring from here and I open it up, this is how it would look like. This width will be delta x, and this length will be 2 pi x, actually x plus delta x. And this part will not be actually rectangle because the inner ring is smaller. It would be something like this, a trapezium. But we could again assume that delta x is very small, almost zero. In that case, this would be, we could assume that this is a rectangle, and we could, for simplicity, assume this also, that this is 2 pi x. In that case, where delta x is almost zero, we have what we have done is we have taken this ring and we have put it like a rectangle. I could continue doing this both inside and outside, more such rings. So we will have more rectangles like this. As you go outside, the rectangles will become bigger, taller. This is the last rectangle, let's say. As you go inside, the rectangles will become smaller because of smaller radius. This is the, let's say, last rectangle. Last rectangle will be at the center, height 0. When you go inside, when you go outside, the last rectangle is this, whose height is length of the this outer circle, which is perimeter of the circle, which is 2 pi r, right? And I could draw it like this. Again, if delta x is almost zero, these steps would not look like steps. They'll become continuous lines because delta x is almost zero. In that case, this becomes like a triangle, right? What is the base of the triangle? This length. This is starting from center. We have gone till the last rectangle, which is here. Starting from center, delta x, delta x, delta x, delta x. This is the width, delta x, right? Delta x, delta x. Sum of all these widths, which is radius. So this is radius. And if I have to find the total area, A will be, we know that this is a triangle. Area of a triangle is half base, which is height, base r into height. Height is 2 pi r. Again, 2 and 2 cancel out, and we get pi r square. This is another way where we have divided the original circle into many rings, and we have placed the rings such that they form a triangle. And we have proved that the area of triangle is pi r square. This should be same as the area of circle also, because this triangle was constructed from the rings in the circle, right? This is the second way using which we have proved that the area of circle is pi r square. And again, we didn't use calculus, correct? let's move on to third way. Again, we will not use calculus, and we'll prove that the area of circle is pi r square. This is third way. Let us say I can divide this circle in two parts like this. Let's say I call this as red part, and I could say this is black part, just for understanding. I could further divide this circle in two more parts. Now, if you look at these four parts, they are identical. This is the center. These two are diameters. These four parts are identical. They have same shape, size. Their areas are all same, right? I could continue doing this. I could divide these further. Now those four shapes have been further divided, and now we have in total eight shapes. One, two, three, four, five, six, seven, eight. These eight shapes are identical because what we have done is we have drawn lines. These are diameters all passing through center, and these angles are all same. So these are identical shapes. These are like slices. What I could do is I could rearrange these slices. So, and if I in any way I arrange these, the area of those rearranged figure and the circle will be same because it is made from that. So let's see. If I arrange it like this, one, two, three, four. This is the red part. This part. Okay. This is how it would look like. All four red slices. Their areas. Now I could take these four and put it like this, inverted. One, two, three, four. This is how I. If you closely look, this arc's length, this upper part, this is this length, which is pi r, half of perimeter. This is 2 pi r, this part is pi r. And if you look at this part, this length is r, radius, because this slice, right? So all I have done here is I have taken these shapes and arranged those in a way such that the circle is broken into, it looks something different. And these lengths, this length is pi r and this radius is r. This length is r. This is not vertical. This is slightly horizontal, slightly slanted because of the shape of the slice. I could continue doing this. I could divide these further, all these shapes into further small pieces. In that case, what will happen is these four parts, all of these would become smaller. This would become like those slices would look like this. These are eight slices, each one divided into two. And this is how the black part would look. 5, 6, 7, 8. Right? Again, this is the red part, and this is the black part. Eight parts. This length, this curved length, this is still pi r because we haven't done it. We haven't changed anything. All we have done is we have split these into multiple parts. Each of those into two parts. This length is still pi r. This length is still r. Right? I could continue doing this. Divide this further. Then divide these further. And further. Continue. Each slice broken into many small pieces. What will happen in that case if we break into let's say infinitely many pieces? These curves, what is a curve right now, would become like 2 points next to each other, and this is how it would look like. This. It would, in a way, what would happen is it would look like uh, they would almost become like a straight line. They are this straight line is composed of many small curves like this. And because those points are very close, that curved length is so small that it's almost like a straight line. If this curved length is like a straight line, then this two become straight line. This becomes R. This length, actually, this is black part. So upper part was red. This part is black, based on how it's split. And this length will still be pi r, same as this pi r, right? Because all we have done is we have taken these slices and broken them into many small pieces. The area of this part is pi r square because it's the rectangle now. Pi r length, r width, breadth. So pi r into r, pi r square, which is same as the area of circle. So this is a third way where we have broken this circle into many small pieces and rearranged those pieces so that they form a rectangle. In the first case, we had broken into many small triangles. In second, we had broken them into rings and then rearranged the rings so that they form a triangle. In the third, we have broken them into slices and rearranged the slices so that they form a rectangle. In all three ways, howsoever we arrange, we have found that the area of circle is pi r square. Correct? So these are three different ways where we haven't used calculus, and we have proved that the area of circle is pi r square. These are clever ways to prove. There is a simpler way. If you know calculus, I can complete that also for the sake of completeness. So this is using calculus. Let's say you have a circle of radius r. Its area is something that we need to find. I could draw a smaller circle of radius, let's say x, and if I draw another circle of radius x plus dx, then this width will become dx. Then area, small area dA will be 2 pi x dx. 2 pi x is the length. If you open it up, it's again like a rectangle, and dx is the breadth. If you open it up, 2 pi x is the length, perimeter of the circle, and dx is the height, width. So dA is 2 pi x dx. I can integrate this from 0 to a, from 0 to r. X is from 0 to r. This becomes a, and this is 2 pi comes outside, x dx 0 to r is equal to 2 pi r square upon 2. X dx is x square upon 2, x square upon 2, 0 to r. This is 2 pi into r square upon 2. 2 and 2 again cancel out, and it cancels pi r square. So here, what we did is we used advanced mathematics, we used integration to prove that the area of circle is pi r square. In the first three, we didn't use integration, we didn't use calculus. We used clever ways to prove that the area of circle is pi r square. Okay, thank you for watching.